Hey everyone, it's Savannah. I wanted to do a video today where I did my makeup, talked about what's on my face, and then talked about what's on my mind in regards to astrophysics. I was hoping to find a better way of how to blend my makeup with my astrophysics. I thought maybe it might be impossible to combine astrophysics and makeup smoothly into a coherent channel. But then I realized there must be a way to combine them because that's what my life is about, and clearly I exist, so there's got to be a way. I decided that I would try to view this as more of a video journal almost, where I talk about whatever mysteries are bothering me at the moment and share the art that I do on my face every day. With that being said, I'm going to get started with my e.l.f. Luminous Putty Primer. As usual, that is upside down. It's beautiful. And what is on my mind today? What is on my mind today is the question of nucleosynthesis. This is the process by which the chemical elements first originated in the universe. This has been a topic that has fascinated me for quite a while because astronomers only ever really deal with two elements, hydrogen and helium. In fact, there's this funny picture of the astronomer's periodic table. I'll put it up. The vast majority of the universe is comprised of the most simple atom there is, hydrogen. Yet, on Earth, we're surrounded by so much more than just hydrogen. We have, almost 100 naturally occurring elements in the periodic table, and yet when you hear about how stars burn, you'll only really ever hear about them burning hydrogen into helium. So where did the rest of them come from? Now, the obvious place to start this conversation is with the Big Bang, right? The Big Bang refers to a leading theory of the creation of the universe and what happened. Now, the word Big Bang the phrase Big Bang really bothers me because a Big Bang, that's obviously reminiscent of an explosion. And when we think of an explosion, right, it's something spreading out, right? But the Big Bang didn't spread out into anything. It was space that spread out itself. So it's not really appropriate to think of it as a big explosion. It was just everything banging all at once, simultaneously. And for the first epoch of the universe, well, originally we didn't even have light because everything was so energetic that photons, light particles, couldn't even travel at all without being intercepted by other energy and matter and everything in the elementary particles. So for the first 380,000 years of our universe, the universe was completely, well, you could either think of it as completely dark or completely light. Light wasn't able to travel, so we consider that to be opaque. And eventually things calmed down enough for the simplest atoms to form, which began off as just hydrogen, the main form of hydrogen just consisting of one proton and one electron and no neutrons. While hydrogen formed in great abundance in the early universe, so did another isotope of hydrogen. Now, just to remind you guys that isotopes are versions of the same chemical element that have a different number of neutrons. So the way we classify different elements is actually by the number of protons, not by the number of electrons and not by the number of neutrons. Because if you have an atom with the sort of improper amount of electrons, that's going to be an ion, it's going to be a net charge. And if you have an atom with different numbers of neutrons, it's going to be what's called an isotope. But in order to be considered the same chemical element, it has to have the same number of protons. So hydrogen refers to any atom really that has just one proton. So also in the early universe, we formed a certain amount of the universe formed a certain amount of deuterium, which is a hydrogen atom that has one extra neutron, or has one neutron. I'm going in with two-phase Cocoa contour. The abundances in which these formed can tell us a lot about the early universe. And by observing today, what ratio of deuterium we see to hydrogen, we're able to deduce, more where we came from in the story of the evolution of chemical elements. Becca bronzer. So from the Big Bang, the original creation of the universe, the origin, the beginning, I don't know, it's so hard to come up with an exact way of how to explain the Big Bang because it wasn't a birth, it wasn't an origin, it wasn't a creation, it was something. It's hard to say exactly. I'm not sure what the exact right word is. I guess beginning of the universe, since that's when we consider time to have started. So if the universe begins when time begins, then yes, the Big Bang is the beginning of the universe. Yeah. Anyway, in the Big Bang, in the aftermath of the Big Bang, the only elements that were created were hydrogen, which is 1 proton, helium, which has 2 protons, and lithium, which has 3 protons. Now, much more hydrogen was made than helium, and only very trace amounts of lithium were made. All of the rest of the elements, had to be made in different ways. Eventually, when the universe cooled down enough for matter to start condensing, we had giant molecular clouds of hydrogen, so big gas clouds, that started to collapse gravitationally and form protostars, the very beginning of stars. Now, once these protostars had accumulated enough mass, they began to start nuclear fusion in their cores. Nuclear fusion is when two nuclei of different atoms actually fuse together to make a heavier atom. And what keeps the star from collapsing on itself gravitationally is this outward pressure created by nuclear fusion. When two atoms fuse under nuclear fusion, the resulting atom actually has a very small amount less mass than the two original atoms that combined. Now, according to Einstein's famous formula, E equals mc squared, mass and energy are related to each other and are essentially the same just by a difference of the square of the speed of light. So E equals mc squared means that energy and mass can be converted back and forth to each other. A very small amount of mass creates an extremely large amount of energy. A very large amount of energy can create a very small amount of mass. So when you have two atoms that fuse together and the final atom is slightly less massive than the two original atoms, that tiny bit of missing mass becomes an extraordinary amount of energy. And what happens is this energy is what we see as starlight, what we see as energy coming off of stars from the sun. And in order for the star to, keep burning and to not just like gravitationally collapse on itself, it is balanced out by the radiation pressure that's coming from the fusion of the elements in the core. For my eyes today, I'm going to do sort of a blue-green look that I really enjoy. Here's Eel-lectric by Menagerie Cosmetics, Watering Hole by Menagerie Cosmetics, Breaching by Menagerie, and Fluke by Menagerie. Okay, great. So now we've got stars that are fusing hydrogen into helium in their cores. Okay, well, still, where are the other elements? And all main sequence stars, so the majority of stars that we see, are only burning or fusing hydrogen. Well, something really interesting happens when the star starts to run out of hydrogen. We start to burn helium. When helium starts to fuse, it can fuse with itself, or it can fuse with like other hydrogen atoms or with stray particles, and it can be fused into carbon and into oxygen. Carbon is the atomic number of 6, it's got 6 protons, and oxygen is the atomic number of 8, it has 8 protons. So we had hydrogen, helium, lithium, those were created in the Big Bang. And then what about number 4, beryllium? What about number 5, boron? And then we've got carbon, nitrogen, and oxygen. So as you can see, so far we've only accounted for atomic numbers 1, 2, 3, 6, and 8. That's because in nuclear reactions, it is not equally likely for all of the different pathways to occur. For example, we can have 2 helium atoms merge with each other to become a beryllium atom or beryllium nucleus. However, this isn't nearly as likely as helium atoms merging to become carbon nuclei. When hydrogen burns in the center of stars, it burns at a very steady rate, and it's pretty constant. And it, like, let's say a main sequence star like the sun, it might burn hydrogen for like 9 billion years, okay? But then when it begins to fuse helium, it doesn't happen very smoothly. It happens in what we call flashes. So we get these things called helium flashes. As the star progresses in age, it winds up burning heavier and heavier elements at the center of its core. And while that's going on, the burning of the lighter elements doesn't actually stop. It just takes place in like concentric shells throughout the star. So you wind up with like a star kind of like an onion, right? With the outer layer burning hydrogen, and then a slightly inner layer burning helium, and you get down into the heavier elements until you get to the very center. This process continues with the fusion of heavier and heavier elements until we get to iron. And iron is like the ultimate nuclear ash. Okay, so before I was saying that when we fuse 2 nuclei together, 2 atoms together, the resultant product has slightly less mass than what went into it. So that like extra mass is lost as energy. And that's what keeps the star shining, and what keeps the star from collapsing in on itself is that pressure of outward energy. But when it comes down to iron, it takes more energy to fuse them together. Like, we have to input energy in order to be able to fuse them together. So like the final product technically has like a little bit more mass than the 2 constituents that go into it. Means that it's really not energetically favorable for stars to burn anything heavier than iron. So we've gotten all the way down to iron now, but the atomic number of iron is only 26. So what about like literally all of the other elements? So this is what I find truly fascinating and truly interesting, is the origin of everything heavier than iron. A lot of these elements that are heavier than iron are created when the star finally dies. In a massive explosion, we call it a supernova. So when there's enough iron at the center of a star, it no longer can push out against gravity anymore, and so the star begins to collapse really fast, like free fall times, like the outer layers of the sun reach close to the speed of light traveling so fast. We call that relativistic speeds, which is insane. So we're going over billions of years, burning hydrogen and burning helium, and then we get to the very end and we're burning the heavier elements. It takes place on the order of like a day. But to be honest, this is not something I understand all that well, which is why it's on my mind. You know, I look around me and I see things that are made up of, you know, aluminum, and, you know, there's a silicon and cobalt inside my computer and vanadium, but these elements were created only under extremely rare circumstances. And it's fascinating to me to think about the abundance of elements on Earth and how ridiculously different it is from the abundance of those same elements out in the universe. So this is how we're looking with my eye look. It's a simple, easy, no big fuss. For inner corner shade, I'm going to go in with this Purlisse Beauty highlighter in the shade Lucid. It's like a multichrome shifter. Gorgeous. So there are some processes that like I said, I don't pretend to be able to understand in the formation of some of the heavier elements. There's something called the R process and the S process. And that refers to the speed at which these nuclear fusions of heavier and heavier elements take place. The R process is the rapid process, the S process is the slow process. And these are quite complicated. They have very complicated nuclear reaction equations, so this is something that I've been trying to look into more. One question I have, for example, something that I don't understand yet and I need to figure out, is why, if hydrogen, helium, lithium are all created in the Big Bang, or, you know, relatively shortly after, they don't have to be made in stars, why is there so little lithium compared to the amount of hydrogen and the amount of helium in our universe? And I know that, you know, beryllium and boron are not made in the same quantities in stars that carbon and oxygen are, but I still don't quite understand why, and that's something that's very intriguing to me. In fact, this topic is so interesting to me that the screensaver of my computer is actually the periodic table that's color-coded by the origins, the cosmological origins of each element. I'm going to do my other eye and then put on liner and mascara, and I'll be right back. Alright, so I finished off the eyes with my Kat Von D dagger liner and green mascara. You definitely can't tell that it's green on the eyes, but I like to think that it matches my hair better and it seems more natural. I don't know. The real reason I like to use this is because it washes off super easy. And I hate scrubbing my eyes at the end of the day. Okay, for highlight, I'm going to go back in with this boy that I put in my inner corner. This is Purlisse Beauty, the shade Lucid. It's really cool and like shifty and multichrome. Yeah, so anyway, about nucleosynthesis, I wanted to tell a quick story about how earlier this summer I got the chance to attend these webinars called like the Golden Week of Astrophysics, and one of the guys, oh my god, look at that, do you see that? My camera can't even understand it. Yeah, called the Golden Week of Astrophysics, and one of the first lectures we had was this guy named Peebles, John Peebles, and actually, after that I bought his book. I still haven't got the chance to read it, but Cosmology's Century. And this guy won the Nobel Prize. He's awesome. He is like the founder of modern cosmology. But it was so super cool. This is like one of the best things that's ever happened to me. I was on this big webinar, you know, with thousands of participants, and you could ask questions, but you had to like put it in this question box, and then during the talk, like panelists were going through the questions and deciding like which ones were worthy of being asked. And mine was the first one to be asked. I was so happy about it. So I like indirectly got to talk to Peebles, and he's just someone I've looked up to for so long. So that was like really, really exciting for me. Anyway, I asked him, what do you think is the current biggest issue, or the current biggest question in the issue of primordial nucleosynthesis? You know, what don't we know? What are we really looking for? And his answer stunned me. He was like, we don't really have that many unanswered questions. What? I do. I have a lot of questions. But yeah, it's a topic that really intrigues me, and I don't pretend to be able to speak authoritatively on anything I talk about on my channel. I am just a student of astrophysics, just explaining the things that I love and talking. And please, if you guys catch a mistake in what I'm saying, please let me know. For lipstick, I'm going to go with Urban Decay Rapture. So let me know what you guys think about this issue of the origin of elements. Does it intrigue you? Do you not really care? What do you think about the fact that we're all made of stardust? That everything our bodies are made of were created in the centers of stars. You think that's cool? Do you care? Should we care? Let me know. Ugh. I love this setting spray, but it comes out like a really fast. I don't like it. But it smells really good, and it's this e.l.f. Dewy setting mist, and it smells like coconut. Anyway, that's it for me for today. That's what's on my mind. If you're new here, please subscribe, leave a comment down below, like the video. It helps me out, and stay curious, guys.